Hi, didn't see you there. I hope you're ready for some electronics. So it is now time to start playing with our Node MCU v3 and getting to know it a little bit and doing some basic projects. Now, a lot of these are going to be quite similar to what you're going to find in your Chem 327 programming guide. You can find that on Quarkus under Open Labs 2B. I'm going to talk about a few of the examples, walk through with you on how to put together all the leads and connections and sensors that you're going to be using in conjunction with your Node MCU v3. So assuming you've already watched part 2, in which case you already have your IDE all set up and everything is working properly, you're effectively good to go. So all you have to do is follow along with this video, as well as read through the guide in your own time and try some of the other projects to get a really good idea of how to start using this and various sensors throughout the course. And eventually you can start developing your own little cool instruments using these tools. So let's begin with a little bit of a brief tutorial. What do you have in your kit? Well, as you can see in the picture here, you should have all of these components. Starting with, of course, the micro USB cable. Nothing fancy, you're going to use that to plug your Node MCU into your computer. You're also given a set of jumper wires. There are 3 types of jumper wires. You have male-male, which have the pin coming out. Got a little bit archaic names, but I guess they're descriptive. We have male-female, in which you have 1 pin and 1 socket. And then you have female-female, which are 2 sockets. Of course, when you're plugging into something like this on the chipsets on the Node MCU, you're going to be using female plugs, as these are male ends. Next, you have 2 sets of LEDs. One is an IR outputter, or an IR LED, and one is an IR receiver. And we can use that to follow along with the project provided in the guide that is given to you on Quarkus. You have 2 types of resistors. Next up, you have a very simple connectivity meter. Essentially, you have 2 probes that are separated, and only when there's something that is conductive between them will they form a bond and actually measure some sort of signal. Next, you have a voltage comparator. Next up, we have an RGB sensor. This is a little bit more of a complicated board. As you can see, there's much more surface-mounted electronics on this thing, and as such, this is going to require the installation of a library to use. And last but not least, you have your Node MCU v3, the heart, or the brains, more specifically, of the operation. This is where you're going to be doing all of your interfacing with all of these sensors and your computer ultimately. So hopefully you have all of that. If you are missing something, do let one of us know, of course. Otherwise, let's jump in. So what are we going to talk about today? Well, we're going to try to figure out how to utilize some of the provided sensors that you have received. In fact, we'll go through the connectivity probe. Again, very simple. We're going to talk about using the comparator in conjunction with your thermal probe, which looks like this. It's a little silver-ended thing. And lastly, we're going to talk about setting up libraries and using the RGB sensor, which is the most complicated thing you'll have to do when you're getting up and running with these tools. There are a few other examples, but for the sake of having relatively brief videos, I won't be going over them. However, you are more than welcome to challenge yourself and go through them before you start the open lab. And of course, if you have any questions, you're welcome to ask me, and we can talk about it together. One thing that we're going to have to talk about and cover today is the use and installation of libraries. And libraries, in a nutshell, are basically little collections of code that you can use that are designed for specific sensors. Rather than having you program all sort of the complex interactions necessary to get a usable signal out of this, someone has already done the job for you, and you just have to know how to use the library in order to utilize this little tool. And so I mentioned a lot of this content is within the programming, the chemistry kit. And this talks about, how to set up the Arduino IDE. There are additional documents if you just want a more quick start guide, and of course, how to use all of these sensors. Now, I'm going to be following along with this with some deviations. Otherwise, you will be able to take these skills that you've learned here and apply them to your open lab and doing something a little bit more creative than just, simple things that we're going to talk about today. Right, so let's jump in and start talking about using the thermistor interface, or the little temperature probe that you're given, in conjunction with this bad boy, the little voltage comparator. In conjunction with the temperature probe, we're going to be using this voltage comparator to essentially create a little alarm and figure out, okay, is it too hot or is it too cold? Naturally, this is a temperature probe and it's capable of doing a lot more, but what's important to recognize is this provides an analog signal. Now, if we want to turn that into a digital signal, we have to use something like this. So this, in fact, we're going to be using as an analog to digital converter. And how that works, I'll explain in just a moment. But it's good to know that you have 2 inputs on the, on the right-hand side and 4 on the left-hand side. And you have to be very specific in understanding what those do in order to actually utilize this. I will also mention that there is a blue potentiometer, a variable potentiometer, placed on top here, and you will be having to adjust that, so I do hope you have a small Phillips head screwdriver available. Before we continue, let's talk about our voltage comparator. We have two voltages on the board, one from the actual sort of signaling or sensing device that we're using, as well as the reference voltage from the board that we use as a comparison. We can tweak that value by using the blue potentiometer on the actual comparator. How it works is that there is a second LED that will turn on. If this is on, this means that the digital pin on D0 is receiving a low signal, or a 0 or false. It's Boolean, it's a digital signal. If the LED is off, this means it's receiving a high signal, or a 1 or a true. So this is the essence of digital signaling. We have either zeros or ones, ons and offs. So what we're going to do is we're going to explore the code a little bit, understand how this works and why this happens, and then we can go ahead and upload this to our Node MCU and get started with how it works. How are we going to do all this? I mean, this seems like a pretty monumental task. Well, I'll tell you that it's very straightforward. Begin by taking your Node MCU v3, and of course, some of the jumper cables that you're going to be using. In fact, I think you'll be using all female jumper cables, so just keep that in mind. Begin by taking the temperature probe, which will have a little white plastic 2-slot female adapter. You can plug that in to the two sockets labeled plus and minus on the left-hand side or right-hand side, I guess, depending on how you flipped over. And the orientation of that does not matter, so you can plug it in either way. And you can go ahead and do that right away. After you've done that, you can start plugging in the remaining 4 wires. So, there are a series of connections on the Node MCU v3, and they'll either correspond to analog inputs or outputs, or digital inputs or outputs. So we have to be careful of keeping track of what is analog and what is digital, because they're inherently different means of transferring data. The first wire, if we're holding this in this orientation as you see in the picture, is going to be connected to A0. Now this is the analog input or output pin, depending on how you declare it, but it is connected to an analog pin. Next up, we're going to connect D0, which will go to D0. This is the second pin down from the top, and this will be connected to the digital pin. Again, input or output, depending on how we set it. Next up, we have the ground wire. This is sort of, well, we need a ground wire to have any sort of voltage measurement, so we're going to connect that to the ground on your Arduino. You can use either the right-hand side or the left-hand side ground. And last but not least, we need some sort of voltage to use as a comparison, so we're going to connect that to the 3-volt lead on our Node MCU. Now that will always constantly supply a voltage of 3 volts, and that's what is going to be used as our reference voltage in this comparator. All the comparison is done on this tiny little black chip. That is an LM393 chip. It's an op-amp, takes care of all the work for you. All you have to do is connect it in this fashion. After you've done that, go ahead and plug it into your computer, boot up the Arduino IDE, and copy in the code that's provided to you in the Chem 327 manual. Now we're in the IDE. I've copied and pasted the code that was given to us in the manual, but I did make one minor modification that I'll talk about. However, I will go through the entirety of the code just to kind of explain to you what everything is doing. On the first line, we're defining the pin D0 to be called sensor digital pin. Rather than having to type D0 throughout the rest of the code, we can just refer to it as sensor digital pin. Now this might seem counterintuitive, but it is easier to think about it as what it is rather than just thinking about the raw pin numbers. In the setup loop, not much is going on. We're using our serial object to begin serial communication at a baud rate of 115,200 bits per second. Then we're declaring our pin mode for A0 to be an input, an analog input. Then we're defining our pin mode for our sensor digital input to also be an input. This is configuring the D0 pin, so this comment is a little bit wrong. The next thing, after we do the setup, remember the setup loop only happens once, so after that we jump into the loop, and that continues to run as long as this thing has power. In the loop, we're going to create a new variable that is an integer called value, and we're going to use the digital read method, the built-in method in Arduino, to read the value on sensor digital pin. If that value is true, or 1, it's going to print no alarm in the serial monitor, I should say. Otherwise, it's going to print alarm, too warm. Remember what I mentioned about how this thing works. It's an analog to digital converter, so it's going to give you either a high or low signal, a true or false signal. In the case of this, remember when the LED is off on the board, the second LED, it's going to be receiving a true signal, which means that this conditional will be evaluated and be run. Otherwise, we're going to be running this conditional. Now, if you notice in the code that's originally given to you, this is set as alarm and this is set as no alarm. I've swapped it around to have it make a bit more sense with how this thermistor works. Remember, a thermistor is essentially a temperature-sensitive resistor. So I would like you to think about how that works and why this conditional and this digital format of readout works. So what I've done is I've gone ahead and verified my sketch, just as I would with anything else that I'm uploading to this thing. I can see I have no problems. There's plenty of memory left over after I've verified this. And then I can go ahead and hit upload. Fantastic. Everything's uploaded. My Node MCU is nicely set up. If you have your code uploaded onto your MCU v3 and you're ready to go, remember we're going to have to open up the serial monitor because we're using the serial objects to do serial communication between the Arduino and our computer. But we have to interpret that data somehow, and that's why Arduino has a handy-dandy built-in serial monitor. Now, I got to this by hitting Tools and Serial Monitor. Alternatively, if you're on Windows, you can hit Control-Shift-M to open it up. Okay, so we can see that right now we're printing no alarm, which means that this conditional if value is being triggered, right? So we're getting a signal of 1 or a high state right now, and the LED is off. This makes sense based on what we learned about this voltage comparator. Now, if I take my sensor and I start warming it up with my hands, now I've already tweaked the potentiometer to set a threshold for myself, so you might have to do this at home. You'll see that as I apply warmth and heat to this thermistor, eventually it's going to say alarm to warm, and the LED on the comparator has gone on. We are now receiving a 0 or low or false signal, and we're triggering the else part of the conditional. Now if I let it go and wave it around a little bit to try to cool it down, you'll see that eventually this will revert back to no alarm. There we go, and that's it. So that's you using the voltage comparator as a simple analog to digital converter with high and low signals, or ones and zeros, trues and falses. Hopefully that makes a bit of sense to you. Otherwise, feel free to ask me questions when you have a chance. Okay, so you're asking, Cam, you know what, this is fantastic, I love comparators, they're super exciting, but what if I just want to read the value of this guy, right? Well, that's where we can just use this as an analog device. This is a thermistor. Of course, it's going to have a resistance, and that's going to be affected by temperature. So in your Open Lab, you'll have an opportunity to use this as an analog device and measure an analog signal from it. And based on the spec sheet that's given for this, you're going to be able to determine roughly what temperature it is, or at least sort of the relative change in temperature. So don't worry, you might not be able to do it exactly with this initial stepping stone on how to set up all these sensors, but you will have a chance to do that soon. So, good question. Let's move on to the next topic. Next up, let's use the comparator. Not as a comparator, but as sort of a resistor inline with our analog sensing device. Of course, if we're measuring an analog signal, we're measuring a voltage, and depending on how strong you want that voltage, or sort of the range of voltage that you want, you're going to have to use a resistor to attenuate that. So what we're going to do today is we're going to basically exclude the digital output part. We're not going to use the comparator as a comparison. We're going to use it as an inline resistor using sort of the potentiometer that's built into it. So what you're going to do is you're going to get your Node MCU v3, you're going to get your comparator, and you're going to get your little connectivity or your moisture meter. Looks something like this. I've currently got it plugged into my computer, but you can see it on the far right hand side right there. What we're going to do first is connect two female-female jumper wires from the two prongs on the connectivity meter onto the two prongs, the plus and the minus, the only two that are just two, on the comparator. Next, we're going to connect up the other side to our board appropriately. First, we're going to connect the A, or the analog output, to A0 on the board. Of course, we want to use this as an analog input so we can read the value, but again, we have to connect it to an analog pin. Next, we're going to connect ground to ground and our voltage to the VCC pin on the comparator. I'm going to let you do this yourself, and I'm going to just jump to the Arduino IDE. You can follow along with this code, it's provided to you, but we're not going to spend as much time talking about this because you have so much time to play around with this during your Open Labs, and we have so much more time to talk about this during office hours and stuff like that. So let's go ahead and jump to the IDE and show you how it works. Boom, we're back in the IDE. We have some new code here that we're going to walk through quickly. Again, this is available for you. And then we're going to go ahead and upload it onto our Node MCU v3, which has already been configured in the way I've just shown you. So what we're going to do first in our setup loop is simply just invoke the serial object and use the begin method to declare that we want a 9600 bits per second baud rate. This is different than before, but again, this doesn't matter. We can select. In fact, I think the Node MCU v3 prefers this baud rate, so we're going to go with that. In the actual loop that we're using to sort of read the value, we're going to do a very similar process. We're going to create a new variable called sensor value that is an integer, and that is going to use the method analog read to read the value out of A0. Now, we haven't defined A0 up here because we don't need to. We can if we'd like to. In fact, I'll show you. So we can say analog pin, which is the name I've given, is defined as A0. And now down here, we can call this analog pin. All that this program is going to do is read out this value, and in the serial monitor, print the value of sensor value. And of course, since this is just two prongs separated, if there's nothing there or air, there's very minimal resistance, so we're going to get a larger value or a larger voltage. Now, if we introduce something that's conductive, like let's say a bottle of water, we'll see that that value will go down. So let's go ahead and try that by verifying our sketch real quick and uploading our sketch onto our Node MCU v3. Fantastic, it's uploaded, it's running. Now let's go into the serial monitor as we did before to read out this value. Keep in mind that values in terms of their analog readout on the A0 pin are likely going to be 8-bit, meaning that they're going to have a minimum value of 0 or a maximum value of 1024. So let's go to Tools, Serial Monitor, and ensure that we've got 9600 baud. And we can see that we're reading our maximum value right now, 1024, right? I mean, there's just air separating these two prongs. We don't expect there to be much conductance, and so our signal is going to be very large. And that's how we know how to use this sensor. We know that we're looking at something that is a large signal, meaning that there's little moisture or conductance, as opposed to a small signal when there is something to facilitate conductivity. So let me go ahead and take my trusty Nalgene, and I'm going to dunk in this sensor. And there's full of water, just regular tap water, and you can see that the value starts going way down. Now we're reading 400, right? This is because now there is connectivity between these two things, and we're reading a value. We can, of course, fine-tune how this works by using the potentiometer on the comparator, but we're not going to do that right now. So this might give you some ideas. Okay, I'm just using tap water, but what if I wanted to use juice, or what if I wanted to use salt water? You're going to be able to do a whole lot of comparisons about certain properties using a very, very simple analog setup just like this. So without saying much more, you can discover more in your open labs. Now we're going to start talking about the TCS34725 RGB sensor. As the name implies, this is a sensor for sensing red, green, and blue light, and it has outputs for each individual channel, so you can sort of track how much red or how much blue is in a particular light that you're looking at. This is actually a really cool sensor. It is a digital sensor, and as such, we're going to be using digital measurements. This is vastly different than what we were doing with analog measurements, but keep in mind that there are two schools of thought when it comes to measurement. Do you want to do an analog measurement, or do you want to do a digital measurement? This thing is quite complicated in terms of its composition and sort of what the electronics on board are doing, but you don't have to worry about that. All you have to do is install the library for this in your IDE before you get started. So, the sensor, as I mentioned, has 4 light-sensitive channels. It allows you to measure red, green, blue, as well as clear or white light. And before we can even start connecting this, and I can show you the wiring diagram for all this, we have to install the library for this in our IDE. So let's quickly jump over to the IDE. Okay, we're in the IDE, just a blank sketch. Don't worry about filling any of this in for now. All we're going to have to do for now is just hit Tools and Manage Libraries. From here, we're going to open up a little window. It's going to update really quickly. Effectively, this connects to the internet and looks at a repository of different libraries. So all you have to do is search the appropriate one. I'm going to go ahead and search for the Adafruit TCS34725. I'll find that it pops up here. Of course, we're going to select the newest version and hit Install. Perfect. That's taking care of installing the library for us, but we haven't connected that library to our code yet. And we're going to go ahead and do that after we talk about how to wire this thing up. Great. So we're back, and we're going to talk about wiring once again. So take your Node MCU v3 and take your little RGB sensor. We're going to connect things based on what I'm going to call them on the pinouts, or the little labels that you see on the various different electrical pins on the sensor, and how they connect to the individual sensors on the Node MCU V3. So first things first, you're going to take a female-female jumper cable, as both of these have male pins on their ends, and you're going to plug the pin labeled SCL into the D3 pin on your Node MCU. Next, you're going to take a female-female cable and connect the pin labeled SDA on the sensor into D2 on the Node MCU. Next, and also optionally, but for now, please do connect it, you're going to connect the pin labeled LED on the RGB sensor to D4 on your Node MCU, again using a female-female jumper. Lastly, we're going to connect ground using the same method, so of course we need a ground for everything, and V-in. Be careful not to connect 3V3, that's actually a 3.3 volt source off of this board and not off the parent board. So remember to connect V-in, standing for voltage in. And that's it. This is actually a really easy sensor to connect. All we have to do is spend a little bit more time with the code rather than the actual sensor itself. So let me go ahead and show you what that looks like in the IDE and what we're dealing with in terms of code. Back in the IDE, we're finally in the home stretch. I've gone ahead and taken my Node MCU V3 and I've connected it to the RGB sensor as I had described. And I have this code here that's just a simply modified version of the code that you've seen in the programming chemistry kit guide that you found on Quarkus. All I did was get rid of sort of the looping part with the LED turning itself on and off after 10 iterations of the loop. So in effect, we don't actually need to connect that LED pin that I talked about, but you can always, in fact, you should just use the original code to first test this out for yourself to make sure that everything is working before you start modifying things. We're going to start by including our libraries. And so at the very top of the sketch, we can see that we wrote include wire.h and include Adafruit TC-S34725. These are two libraries, the first one being a local one and the second one being a downloaded one, that we're going to use throughout this process. It's important to know that if you want to use a library, you have to somehow include it in your code, and this is the syntax to do just that. We have a little bit of setup stuff here that I'm not going to talk about so much. You've already recognized the serial object and the baud rate that we've assigned here. There's some additional stuff going on in terms of joining buses and stuff that you really probably won't quite understand for now, so you can skip most of that. Again, this is just an example script that you can work with to fully understand and get better with. We don't actually need this line here, so I'm going to remove that. This is basically set up, you're creating an object that's called TCS that is using the library that we've used to basically initialize an object that controls this thing. And then we're going to do a little bit of a test to see, okay, can we find the sensor or can we not find the sensor? That's all going to happen in the setup, so it's only going to happen once. And in the loop, essentially what we're going to do is we're going to collect some unsigned integer that are 16-bit for our variables RGBC, color temp, and lux. These are all then going to be printed out using the serial print command. But to explain to you in a nutshell what's going on, there's a sensor here that has a series of filters. It'll sense RGB and the overall lux, or the brightness of the light that's being applied. And you can use that to essentially get an idea of, how strong your light source is, what kind of colors predominate, and utilize it for whatever sort of sensing or measurement that you want to do. Now this is all digital, of course, because we're using a digital module. So I've gone ahead and verified this and uploaded it to my Node MCU V3, so it's already running, and I just want to show you what it looks like. So again, we're dealing with serial commands or serial printouts, so we're going to be seeing that in the serial monitor. So let's go ahead and go to Tools, Serial Monitor, and we'll see, assuming that we have changed our baud, don't forget that this is a different baud rate than the last example. You'll see that we're getting readouts for the color temperature in Kelvin, the lux, sort of the overall brightness, as well as the values for RGB, C being the overall combination of this. I believe it's some sort of factor of RG and B. I don't exactly know how it's calculated. And lastly, the time. RG and B are pretty recognizable quantities. If I introduce, for example, on my telephone, more red, look what happens to the sensor. So right now we're getting about 60 on the R channel, 49 on the green channel, and 29 on the blue channel. If I put this over here, obviously the lux is going to go up because there's more light, but also look at the red channel. It's much stronger now. The green and the blue are obviously affected because this isn't pure red. This is just some random red image I found on Google. But we can see that it's behaving exactly as we'd expect. Our red value went up, our green and blue is slightly modified, as well as our lux has increased because I've just put a bunch of light there from my phone. So as you can see, this sensor is jam-packed with a lot of potential. How you so choose to use this potential will be completely up to you. So that's all that we have for today. Thanks for bearing with me on this relatively long video. But before we go, I do want to just wrap up a few thoughts. So we've talked about a lot of different concepts today. And I know it might be a little bit hard to wrap your head around certain things if you've never really played around with Arduino or various other microchip controller programming, and as well as dealing with all these sensors and stuff. Now this is just a select few examples, but naturally there's going to be a lot more for you to learn. So what I encourage you to do is to work your way through the provided programming guide kit. I keep saying random words. The little guide that's on the Quarkus that gives you the information on how to get up and running and do some of these example things that we've talked about today. So there's a whole lot of information about there on how to find data sheets for these sensors, how to learn more about what's going on, where can I find better example codes, how can I find other libraries. There's just so much to talk about that we can't possibly talk about it in the course of a 30-minute video. So I want to leave you with this last important statement. In this class, you're going to be dealing with either digital or analog readout. Digital is simple. It's on and off, ones and zeros, trues and false. This is how all of your computers work. It's a massive array of transistors that sort of transmute these signals in order to do complex logic. And so that's often digital. Analog readouts are a little bit more straightforward. You're reading out a value, usually relative to a voltage or something like that. So keep in mind that analog usually has a larger range because you're not reading either on or off or a state like that, you're reading an actual output. So when you're thinking about designing your experiments and as you're working through OpenLabs 2B, keep that in mind about how you'd like to use these sensors, if any, to design your experiment at home. Anyway, that's it for me now. If you have any questions, I'll see you in office hours, and good luck playing around electronics. Bye-bye.